Mathematical induction, an overview. This material is given in an appendix. Mathematical induction is a method of proving that every natural number has a certain property p. So we want to show that for every n in natural numbers, p of n holds. We'll be able to conclude this given two things. 0 has the property p, and also for every natural number n, p of n implies p of n plus 1. If these two premises are established, then we can conclude that every number has the property p. The intuition behind the mathematical induction is as follows. We establish p of 0 and also this universal statement. This universal statement covers the following cases. P of 0 implies p of 1. P of 1 implies p of 2. P of 2 implies p of 3, and so on. Now, think about just using the logical rule of modus ponens. If we know p of 0 and that p of 0 implies p of 1, from these two facts we derive by modus ponens that p of 1 holds. Now, given p of 1 and that p of 1 implies p of 2, by modus ponens we derive p of 2. Given p of 2 and the fact that p of 2 implies p of 3, we derive that p of 3 holds, and so on. And this is an intuition behind the proof method of mathematical induction. This is not a formal argument of any kind. Now, let us take an example. We are going to prove that 1 plus 2 and so on plus n equals 1/2 times n plus 1. Proofs by mathematical induction have one standard form. I have prepared an outline right here. Let's go through the outline first. We'll say proof by mathematical induction. Consider property p of n, and we still need to specify what property we are considering. We need to prove that for every natural number, p of n holds. There will be a base case concerned with establishing p of 0. This corresponds to what we mentioned earlier. We want to show that p of 0 holds. There will be also inductive case in which we will show that p of n implies p of n plus 1 for every value of n. To accomplish this, we will handle the universal quantifier as usual in proofs. We will say take any n in natural numbers. Now it remains to show the implication p of n implies p of n plus 1. So our inductive hypothesis will be assume p of n. Our goal will be p of n plus 1. And some work needs to be done to show that such a goal can be reached. So now let's see how we can use this template to provide a proof of this proposition. Our property p of n is that 1 plus 2 and so on plus n equals 1/2 times n plus 1. In the base case, we'll show p of 0. So we need to consider what this kind of statement means in the case of n being 0. The sum on the left-hand side of equality, in such a case, contains no terms. The sum with no terms has the value 0. And the value on the right-hand side will be 1/2 times 0 times 0 plus 1. This equality is obviously true, so there is nothing else to do. In the inductive case, our inductive hypothesis is that the equality holds for a particular value of n. So this will be 1 plus 2 plus n equals 1/2 times n plus 1. The goal will be that the equality holds when n is replaced by n plus 1. In such a case, our equality takes this form. The sum this time extends up to n plus 1, and on the right hand side I have this kind of expression, but n is replaced by n plus 1, so n plus 1, and then n plus 1, which is n plus 2. Now it remains to argue that the inductive hypothesis implies the goal. So we will say the following. Notice that 1 plus 2 and so on plus n plus 1 equals. I'm going to take a look at this part of the sum, and by the inductive hypothesis I know that it is equal to this expression. So the sum is equal to 1/2 times n plus 1. And of course I need to account for the term n plus 1. Now I can factor out n plus 1 from the sum, obtaining 1/2 n plus 1 times n plus 1. And this in turn can be rewritten as 1/2 n plus 2 times n plus 1. So please notice that 1/2 times n plus 2 gives me exactly this. By distributivity I get 1/2 n, and then 1/2 times 2, which is 1. And now I can just change the order of the factors in this expression, obtaining 1/2 times n plus 1 times n plus 2. So I have obtained the goal, and this ends the proof by mathematical induction. I have discussed mathematical induction for proofs that every natural number has a given property. Sometimes the goal might be to show that every number starting from some number k has the property. In such a case, we use a variant of mathematical induction which can be written as follows. We show that p of k holds, and also that for every number greater than or equal to k, p of n implies p of n plus 1. Given these two facts, we can conclude that for every n greater than or equal to k, P of n holds.